Hello everyone, welcome back to the Wireless Communication and Network Divergent class. We meet again for 5 weeks in a row now. Last week we talked about the introduction to wireless communication. For this week we will talk about the signal propagation and channel models. Now, like every week, the first question comes out of your head is, what is signal propagation? Okay, signal propagation, or in this case, radio signal propagation, is the movement of radio wave from a transmitter to a receiver. When the waves travel or propagate from one point to another, they are like light waves affected by different phenomena such as light reflection, absorption, or scattering. Well, how does it work? In the telecommunication system, there's a part called as modulation. Modulation usually modulate the information which is in binary form. The output of the modulation is analog signal. The analog is in complex number form. The analog signal is usually amplified or shifted to the frequency carrier, for example, Wi-Fi. In this case, the analog signal will be shifted to 2.4 gigahertz, and then the signal is transmitted to the antenna. At the receiver, the signal is written in mathematical form as yt equal to ht. Channel is important in wireless communication because any received signal is affected by the channel. Thus, it is important to know the propagation characteristic, which is the next topic we will talk about. There are three propagation characteristics, which are path loss, shadowing, and multipath fading. To help you understand about those characteristics, I'll try to explain to you with a picture. An antenna transmitter will transmit the signal to the car as the receiver. The first propagation characteristic, which path loss, is described in blue lines. It means a direct straightforward path forward towards the receiver. We characterize the propagation by finding the ratio of the received signal to the transmitted signal over distance. From the graph, the blue line represents the path loss. We see from the blue line there is a very slow change in this ratio. The second propagation characteristic, which is shadowing, occurs due to obstruction from an object. Red block or wall here represents the object. The object affects the signal because it has minor fluctuation, which is different from the blue line. The third propagation characteristic is multipath fading. Is the signal that goes to the receiver comes from many different paths or reflection. From the graph, the green line represents multipath fading. It shows the fluctuations are more frequent than the red ones. The ratio is not exactly consistently decreasing. Next, just like the title of this video, we will talk about its modeling. For path loss modeling, there are several path loss models. The first one is Maxwell equation. The second one is free space and path models. The third one is ray tracing model. The fourth one is single slope path loss exponent model, and the last one is the measurement base and standard models. The signals are consisting of electromagnetic wave. The first path loss model, Maxwell equation, describe the interaction between the electric field and magnetic field, which is combined together to become electromagnetic propagation. However, it is quite complex and impractical. So there are modeling methods that has easier to use, which is free space and two-path models. The free space model describes the propagation of signal without facing any obstruction to the receiver. In general, the free space model characterizes that power falls are proportional to the distance squared inverse. It is proportional to the wavelength squared and is inversely proportional to the frequency squared caused by the effective aperture of the antenna. And on the right side, the two-path model. In the receiver, receives two types of signal, which is the line of signal or LOS and the non-LOS signal. The non-LOS signal came from refraction. In this model, the power false is proportional to the distance squared, and the power decreases significantly when the distance is further than its threshold distance. It also states that it is independent of wavelength and frequency. Next is the ray tracing model. It takes reflection, scattering, and diffraction phenomena. From the picture here, red lines are reflections, blue lines are scattering, and the green line is diffraction. Since there are many reflection or fraction, the receiver may receive many signals. The model requires site geometry and dielectric properties. Well, it seemed really confusing and complicated, but there is a way to make it more simple. So there is a simplified path loss model. It is the simple version of path loss model. This model is used when the path loss dominated by the reflection and from the objects. This is the equation we can use to model the signal propagation. With dr is the receiver location, d is the reference to the receiver location, dr is the power is received, and pt is the power transmitted. Next is the millimeter wave. What is millimeter wave? Okay, millimeter wave is the band of spectrum or frequency bands that lies between 30 gigahertz and 300 gigahertz. This is due to the fact that the wavelength of the electromagnetic wave will be in the millimeter range at this frequency range. Millimeter wave is located in high spectrum bandwidth. Next, the picture above start from the top left, which is the lowest frequency spectrum, to the highest frequency spectrum, the bottom right. In the US, the 5G is located in the 38 gigahertz spectrum. However, currently only a few commercial millimeter wave systems occupy this frequency. Millimeter wave still needs more research, since its channel model are still immature based on the measurement and few accurate analytical models. The path loss proportion to wavelength square is enormous, and it has oxygen and rain absorption. So what? We got another problem here? Don't you worry, we have a solution. And the solution is, hit drum roll, is the empirical channel model. In the area which is not suitable for millimeter wave, the existing channel modeling cannot be used. The early cellular empirical models are based on extensive measurement. The example are the Okumura model, Hatta model, COS 231 model, multi-slope model, Wafish-Bertoni model, and etc. However, the Doppler model is dependent on its location. Well, that's all, folks. See you next time. Thanks for watching.